some background here. If they go to a help screen, it'll give them background on a lot of the terminology as well. But to bring you up to speed a little quickly on that, I've got one of my Connex bridges modeled here. And the truss portion that we're talking about, there's actually two of them here. We've got a truss is a two-dimensional structure. We're looking at where it carries loads in a two-dimensional plane. We're looking at one truss on this side, an identical truss on that side. The roadway, assuming that I were to set this truss up, and I'm going to borrow the backs of your chairs if you don't mind. If I'm going to set the truss up like this to span across the river gorge, I would be supporting the truss on what's referred to as abutments, is the term we'd use at these ends. Here's my span, and the way I've got this set up here is this truss would be what we would call a through truss. We'd build the roadway, the bridge, this is the bridge deck. We'd build the roadway through the truss and the traffic would run through there. The other way is to build it as what's referred to as a deck truss. And here I'd probably just turn it upside down, and I'm going to have a hard time doing that because these chairs aren't far enough apart. But I support here and I support here, and then the traffic will run across the top when we build the roadway on the top. And then of course you've got your double-decker bridges where you've got the highway both top and bottom, and then you need to build the what we would refer to as the approaches that would allow us to channel the traffic where we want it. Okay? But the big thing to see is that this portion of the structure and that portion of the structure are two identical trusses that are supporting my roadway. Okay? What I see here in red are what I would refer to as my chords. The bottom chord, the top chord. Okay, now what is going to happen is with a truss, it carries the load as directly, is probably the best term I can use, in either tension or compression, not in bending, not like a beam would carry it. In a way, behavior models the beam in that as we put the load on the truss, that truss is going to flex a little. In doing so, what's going to happen is the bottom chord members are going to be stretched out in tension. The top chord members are going to be put into compression. Okay? The yellow members you see here are the diagonals, okay, which are also going to be in tension or compression. And that can alternate, depends upon the geometry of the truss and where the loads are applied. And sometimes one member might be in tension, and then the loads move elsewhere on the bridge, and that member could go into compression. So they can experience both. My purple are the joints. The joints are where we connect the truss members together. Anybody remember the I-35W bridge out in Minneapolis, the collapse they had while they were constructing it? That was a joint problem. In particular, the problem with it was that the gusset plates weren't properly designed. Gusset plates would be the term we would use for the plate that's used where the members are then all brought together in that single location and connected.
They're fixing that then?
They have fixed it, yes. Yes.
But it was built, and they were using it all the time, didn't it?
Yes, what they were doing. The problem was, as is the case with any engineering failure, okay, it is rare that there's a single event that leads to a catastrophic failure. Normally what it is a succession of what I call mishaps, any one by itself that would not have created failure, but it's called Murphy's Law. They go wrong, you know, kind of domino effect, right? You get a bunch of things that go wrong and then you get a failure. The problem started back with the actual design of that truss bridge. They did not follow recommended, those gusset plates were about half as thick as they should have been according to the design criteria of the time, okay? Design criteria at the time was probably not as conservative as it should have been, okay? And then they misapplied that design criteria. Even still, that bridge held for years. They were in the process of doing some deck work and were funneling the traffic into one lane, and they had piled the construction materials they were using for the deck work they were doing in the absolute positive worst location they could have put it, okay? And so it took all of that to create the failure. And it was interesting to me because my PhD dissertation was on stability of the gusset plates in truss-type connections. So I got a flurry of interest in my PhD dissertation after that bridge collapse. Everybody wanted to take a look at it because we kind of went back and re-looked at how we did gusset plate design back then. And there have been some recommendations that have come out of that, and some looks taken at gusseted connections in truss bridges, you know, all over the place since then. So, at any rate, I provide the physical model so we can talk about what we mean. Bottom chord, top chord, diagonals, the joints, okay, which would be gusset plates. And then the other thing I want you to see is that when I look at what would be my bridge deck, okay, these orange members, they're what I would refer to as floor beams, okay? We're going to build the highway on top, the bridge deck on top of this, supported by floor beams, which take the loads of the highway, the roadway surface, and distribute them to the joints of the truss. And then I've got gray members in here, okay, that kids don't always, and it's funny, when I do the summer camp and I'll talk to them about the importance of this, and they're so focused on building the truss itself and making that good and strong, they neglect the need to provide for, the truss is carrying the gravity loads, they neglect the need to provide for lateral stability, okay, and they'll leave these members out. And, you know, we talk about why is a truss bridge built the way it is? Because that triangular shape is one of the most stable shapes we're going to come across. And then when you get rid of it, like they will forget about laterally, they end up with their bridge deck. You can see how easy it is to wrap on them. And they'll load it, and they're so proud of it. And then what happens is it skews on them and twists and breaks apart this way. So I'd like to talk about the importance of the lateral bracing to provide that stiffness, not just in the vertical plane, but also in the horizontal plane too. Okay. The software you're going to work with is going to design only the truss itself for the gravity loads. Okay, but you know we got to start somewhere, so we start with that. And then if we're building from that, it's important to bring in some of these other criteria. The other thing it does, that the software we're using, designs only the members themselves, okay? And I like to point out to the students the importance of the connections. Certainly the story of the I-35 West Highway Bridge kind of points to the importance of the connections. And I'll indicate we tend to have more problems with failures with connections than we do with members. Why? We pay way more attention to our member design than we do our connection design, the importance of the details with the connections that we're building. But the software you're going to work with is just going to allow them to design the